It's often said, and I think this was started really by the late David Schramm, that today we're in a golden age of cosmology. And that's really true. Cosmology is really, at this present time, undergoing a transition from being a bunch of speculations to being a genuine branch of hard science where theories can be developed and tested against precise observations. One of the most interesting areas of this is something that I've been heavily involved in, predictions about the fluctuations, the non-uniformities in the cosmic background radiation. We think of this radiation as being the afterglow of the heat of the Big Bang. And one of the remarkable features of this radiation is that it's incredibly uniform. We now know that it's uniform in all directions to an accuracy of about 1 part in 100,000 after you subtract a term that's related to the motion of the Earth through the background radiation. I've been heavily involved in a theory called the inflationary universe, which seems to be our best explanation for this uniformity. The uniformity is hard to understand. You might think initially, and at some point I think people did think this, that maybe it was just the same tendency of a hot slice of pizza to get cold when you take it out of the oven, that things tend to come to a uniform temperature. But once the equations of cosmology were worked out, and people were able to do calculations about how fast the universe was expanding, when, and so on, people were able to calculate how much time there was for this uniformity to set in. And what they found is that in order for the universe to have become uniform enough, fast enough, to account for this uniformity that we see in the cosmic background radiation, information would have to have been transferred at approximately 100 times the speed of light. And according to all of our theories of physics, nothing can travel faster than light. So there's no way that this could have happened. So the classical version of the Big Bang theory had to simply start out by assuming that the universe was homogeneous, completely uniform from the very beginning, just as part of your assumptions about the initial conditions. The inflationary universe theory is an add-on to the standard Big Bang theory, and basically what it adds on is a description of what drove the universe into expansion in the first place. In the classic version of the Big Bang theory, that expansion was just put in as part of the initial assumption, so there was no explanation for it whatever. It was never really a theory of a bang. The classical version of the Big Bang theory is really properly described as a theory about the aftermath of a bang. Inflation provides a possible answer, and now it looks like it's almost certainly the right answer, more or less, to the question of what drove the bang, what made the universe bang. And the answer is that it turns out that modern particle physics predicts that there should be peculiar kinds of substances which actually turn gravity on its head and produce repulsive gravitational forces. And the inflationary explanation is the idea that the early universe contained at least a patch of this peculiar substance. And all you need is a patch. It could actually be more than 1 billion times smaller than the size of a proton. But once it exists, it takes over by growing due to its own gravitational repulsion and rapidly becomes large enough to encompass the entire observed universe. Now, one feature of this, to come back to what I was mentioning before about the cosmic background radiation, first of all, it smooths everything out because you start out with something which is incredibly tiny, which just doesn't have room to have structure. Basically, it's had enough time to reach a uniform temperature and uniform density for the same reason that the air in the room reaches a uniform density, and if you isolate the room and let it sit for long enough, it will reach a uniform temperature as well. On this very small scale, there's enough time for that in the early universe. Then inflation takes over and magnifies this tiny region to become large enough to encompass the entire universe, again, maintaining this uniformity as the expansion takes place. Now, for a while in the early days, we were very worried that we would get too much uniformity. One of the amazing features of the universe is how uniform it is, but it's still by no means completely uniform. We have galaxies and stars and clusters and all kinds of complicated structure in the universe that needs to be explained. And if the universe started out completely uniform, it would just remain completely uniform. There'd be nothing to cause matter to collect here or there or any particular place. I believe it was Stephen Hawking who was the first person to suggest what we now think is the answer to this riddle. He pointed out, although he did the calculations wrong initially, but he pointed out that quantum effects could come to our rescue here. The real world is not described by classical physics, and even though this was very highbrow physics, we were in fact describing things classically with deterministic equations. But the real world, according to what we understand about physics, is described quantum mechanically, which means deep down that everything has to be described in terms of probabilities. What we see as the classical evolution of a system is really just the average of the different quantum possibilities that the full quantum theory would predict. And if you apply that notion here, at least qualitatively it's clear from the beginning, it gets you where, in the direction you want to go. It means that this uniform density that our classical equations was predicting would really just be the average of the quantum mechanical densities, which would have fluctuations in it. Someplace the quantum mechanical uncertainty would make the energy density a little bit higher than other places. In other places it would be a little bit lower. So you'd have ripples on top of this almost uniform density of matter at the end of inflation. It's possible to actually calculate that. I should confess that we don't yet know enough about the particle physics to actually calculate the amplitude, is what we call it, of these ripples, the intensity of the ripples. But what we can calculate is the way in which that intensity depends on the wavelength of the ripples. There's ripples of all sizes, and you can measure the intensity of ripples of all sizes. And you can discuss what we call the spectrum, which is, we use that word exactly the way it's used to describe sound waves. When we talk about the spectrum of a sound wave, we're talking about how the intensity varies with the different wavelengths that make up that sound wave. We do exactly the same thing in the early universe and talk about how the intensity of these ripples in the mass density of the early universe varied with the wavelength of the different ripples that you were looking at. And today we can see those ripples in the cosmic background radiation. And the fact that we could see them at all is an absolutely fantastic success of modern technology.